Okay, let's start. So, in the last class, we briefly looked at the Miller compensation. So let's just quickly recap the results and move on. So this is your two-stage. So this is the first stage of the two-stage, and this is the second stage. So let's say this is GM1, GM2. Let us say this is the conductances here and capacitances here. So as such, we know this is not really stable. If you put it in negative feedback, this might not be really stable. So what is the solution to make this stable? What did we do in Miller compensation? You put a capacitor across GM1 or 2? GM2. So let's say I go and put a capacitor here. So let's quickly write the important things for this. What is the DC gain for this? GM1 by G1 times GM2 by GL prime. And let's quickly approximate the two poles. The first pole, as we know, the low frequency pole is due to the Miller multiplication. So help me write the total capacitance here. I have C1 plus, I have this capacitor. What is the contribution of that capacitor? 1 plus the low frequency gain of the second stage, which is GM2 by GL prime. And the conductance there is just G1. And as we saw, for all practical purposes, we can approximate this as G1 by Cc times GM2 by GL prime. Similarly, let's quickly write the high frequency pole. What is the total capacitance here? I have this CL dash and these two combinations, these two fellows in series, that comes in parallel with CL dash. So let me write that. So CL dash plus C1 Cc by C1 plus Cc. And if I look at the total conductance here, I obviously have GL prime. Plus I also have GM2 contributing to a real impedance, which is Cc by C1 plus Cc times GM2. And again, if for all practical purposes, how can I approximate the numerator as? Let's assume C1 is much smaller than Cc. So this becomes GM2. Now I have GM2 and GL prime. How can I approximate it as? I have GL dash and GM2. So which will be greater? Why? What can you say about the DC gain of the second stage? What is the expression for DC gain of the second stage? GM2 by? This is smaller than 1 or greater than 1? This must be greater than 1. So how can I approximate this further as? GL prime or GM2? GM2. Similarly, denominator, I have all of these caps. What will be dominant? If C1 is much smaller, this becomes what? C1. If the load capacitance is the largest capacitor, so this will be dominated by CL dash I'll say is dominated by CL itself. And we also saw this as a right of plane 0, and that is at plus GM2 by Cc. Again, you can clearly check. We have two paths for the current to flow, one through Cc, one through GM2. So we have GM2 by Cc occurring here. And as we notice, this is in the right of plane because the current that is getting pushed through the capacitor and the current that is getting pushed through the GM2, they have different signs, because if this is positive, because of this voltage getting fed to the negative sign, current has a opposite polarity, so this ends up in the right of plane. And we also looked at the unity loop gain frequency. If you assume that this is put in a negative feedback with a feedback factor of beta, how can you approximate the unity loop gain frequency as? It's basically first order. You can approximate that if this is well compensated. Till unity loop gain frequency, it's going to behave like a first order system. For a first order system, we very well know this is the feedback factor times the DC gain times the pole. And of course, you can simplify this. You will find this as beta times Gm1 by Cc. So basically, around the unity loop gain frequency, you can think of it like this. This pushes out the current Gm1 times the input voltage V in. So this current basically flows through this capacitor and gets integrated. So you have Gm1 by Cc. And we also looked at the phase margin roughly. So due to the first pole, you would have already incurred a 90 degrees of phase. So you only have 90 degrees of margin already, of which you have the second pole on the right of plane 0 taking off some phase. So this is minus tan inverse. You need the omega u loop by the second pole minus tan inverse the unity loop gain frequency by 0. And here, let us say, I can simplify this. The ratio of these two, where is this? Ratio of omega u loop by Z1, it is simply beta times Gm1 by Gm2. So if the right of plane 0 is there, you have to choose your Gm2 to be, how should it be compared to Gm1? Gm2 should be greater than Gm1, so that this phase is not so high, right? And if let us say this is kind of not really significant, to get a good phase margin, what can you say about my second pole compared to the unity loop gain frequency? Till the unity loop gain frequency, how do you want the system to behave as? So which means the second pole, where should it be compared to the unity loop gain frequency? It should be far apart. So farther you keep the second pole from the unity loop gain frequency, better is your phase margin, right? If this ratio is really small, then you have a higher phase margin, right? So that's what you're supposed to do. Okay, great. So here, of course, we did the thing we wanted. We added, we make sure that the poles are sort of far apart, but in that process, we kind of introduced an uninvited guest in the form of an RHP 0. And of course, this guest has been there for quite a long time, and people have been looking at this for quite some time. So they've already figured out ways to remove this guest outside the house. And I'll briefly explain one such technique that is commonly used. So first, let's understand the location of 0 once. So let's calculate the location of 0. How do you find the 0 location here? What do you do first? You assume that the output is 0 in time domain or Laplace domain. In the Laplace domain, you make this 0, and then do what? Yeah, you can apply KCL now. So let us say apply a non-zero voltage V in. So which means I have a non-zero current getting pushed out here. If I call this current as I1, maybe I'll use a different color. I'll use this color. If I call this current as I1, what can you say about the current flowing through the capacitor? That is also I1. So we'll make some space. So this current is I1 of S, correct? And if I call this voltage V1, what can you say about the current pushed by the transconductor Gm2? So let me write the current. So first I have the capacitor current I1 of S plus this current. How much is this current? Minus Gm2. Sum of them will be equal to, right? And remember, this voltage is V1 of S. This voltage is at 0. This is the current I1. So what can you say about V1 of S then in terms of the current? Remember that this current I1 is flowing through the capacitor. What is the voltage drop across the capacitor? I1 of S times into SCC, is it? 1 by, right? Of course, now this voltage is 0, so this is directly, okay. So if I write it, now I have I1 of S, so minus Gm2 times I1 of S by SCC. Sum of this is 0. So which means now I know because I applied a non-zero input, this current has to be non-zero. So this means that my complex frequency S must take GM2 by CC, right? The same thing, we have recalculated the 0 location again. So that's how we have the 0, right? So now my job is to make sure that I don't have the 0 in the circuit. Okay. So which means, let us say I try to calculate the location of 0 in the circuit by doing the same process. I assume that the Vout in the Laplace domain is 0 and try to apply KCL. And if I do that and solve for this, that equation should be satisfied for what value of S? I don't want to have 0, which means theoretically where should you want the 0 to be located at? Infinity. Which means if, let us say, there is no 0 here, and then I do the same exercise assuming V out to be 0 and apply KCL, that equation should be solved for what value of S? Infinity. That's the whole point, right? So let's basically so as of now this is what we have, correct? Now I want to make sure this equation is satisfied only for what value of S? Infinity. Now you see that if I put S to infinity, this term goes to 0, whereas we have this term. So mathematically what should change in the equation so that this still gets satisfied? I should somehow add, this should be 0 only at S tends to infinity. If I somehow get rid of this I1 of S, it is fine. Okay. But of course, since I1 is going here, this current is obviously flowing here, so I cannot touch the current through the capacitor. If at all I can change something, what can I change? The current through what I can change? I can change the current through this, and the current pushed out of the GM depends on what? V1 of S, correct? So somehow if let us say the current through the transconductor becomes this, yeah, okay, right? And we already know the current through the transconductor is GM2 times V1 of S. So let me take out GM2 separately. So I'm trying to pull out GM2 from the equation. So which means the first term is I1 of S by SCC. What will be the second term? I1 of S by, some of this will be, so I know this is GM2 V1 of S. So this is GM2 V1 of S. So now we can clearly see what should be my V1 of S now. What from this, what can you say about V1 of S? I1 of S by SCC, and then I1 of S by, yeah, as of now in this particular circuit, V1 is obtained as voltage across the capacitor alone. That is giving me this term. So which means in addition to this, I have to add an additional term here, correct? So what do I do now? Basically, I should have two voltage sources. The first term is the voltage drop across a capacitor. The second term is voltage drop across resistor. What is the value of the resistor? So all I have to do is the following. I don't just have a capacitor now. In addition to this, I go and put a resistor. I'll call it RC, whose value is 1 by GM. Okay. If I do this, now it is clear the equation will get satisfied only for S tending to infinity. So we would have eliminated the RHP 0. Yeah, we'll come to that. It's exactly asking the right questions. So let's address that. But before that, let me ask this, right? So let me keep this here. So here I know that if I keep my, let me erase all this, not needed. So this is CC. So we just saw that if I choose my RC to be 1 by GM2, or I'll do this way. If I had RC to be 0, what can you say about the 0? Location of 0. That was it at? The 0 was at plus GM2 by CC, that was in the RHP. Correct? Now if I keep RC to be exactly 0, where is the 0 now? Yeah. Which means the 0 has been pushed to infinity, which is a good thing. Now that begs a question, what if I make it greater than 1 by GM2? So earlier I had this, the 0 was located here when RC to be yeah.
Shouldn't the 0 go to minus infinity?
Okay, the infinity is already a tricky business. So you think of it this way: you had RC to be 0, right? Think of it as a plotting of locus of the 0. Hmm? When RC was 0, it was infinity. Now if I keep increasing RC, uh, this basically goes here. I mean, if you actually, best thing is you actually take out the, you assume finite RC, that is, don't assume to be 1 by GM2. Find the location of 0 with RC, and then it will be clear. But as of now, let's say it's gone to infinity.
Wouldn't it add unstability? Was it still on the right side?
But it is at infinity, right? Infinity is basically it's non-existent, right? I mean, as of now, you don't have to worry. It is not there, which means you can say it's plus infinity, minus infinity, doesn't matter. If you want to figure out to which side it goes, you have to look at the locus. We'll see that in short. But as of now, let's say it's gone to plus infinity. So if I make it greater than 1 by GM2, what might be a logical guess? Basically, I mean, it turns out it sort of wraps around and comes to the left half plane. And in fact, as I was just saying, if you assume some RC and calculate the location of 0, you will find the 0 to be located at one by GM2 minus RC times CC. So basically, if your RC is 0, this becomes plus GM2 by CC. It is in the RHP. And then now if you see, if you keep increasing RC, it is still in the RHP. It gets pushed, and that's why I'm saying it's actually going towards plus infinity. Okay. And once you make RC to be greater than 1 by GM2, the 0 starts to enter the left half of SP. And left half plane 0 is good or bad? So let me write this enters LHP. So at this point you should be asking me a question. So since you're not asking, I'm asking the question back to you. So since left half plane 0, we know it's already good. Why don't I do this? Why don't I do this and say that I choose a large value of RC and introduce a a good left half plane 0. Maybe I can make sure that the 0 cancels one of the poles in the circuit also, right? Because I know I have 2 poles. I had 2 poles, and now I know that I'm introducing a left half plane 0. Maybe I can cancel one of the poles. Why don't I? Why can't I? I mean, why can't I keep doing this? What approximations? Okay, can you be slightly more? Or think of it this way: if I make RC to be infinity, what happens? So then, do you have Miller effect at all? Right? So in fact, let's see. All this time we have just been looking at zeros. What did we not look at? So how many poles this has now? How would you find the number of poles? I mean, how would you find the number of poles? Number of initial conditions. I can initialize voltage across this capacitor, as well as this now. See, earlier when I didn't have RC, this was sort of shorted. So the moment you initialize 2 voltages, this capacitor voltage got set automatically. But now by introducing RC, you have added an extra degree of freedom. So how many poles will be there now? So now we have 3 poles. Again, to find the location of poles, no shortcut. You just have to solve the polynomial, and you can assume that the poles are far apart. If the poles are far apart, how can you approximate the roots of a polynomial? You can take the ratios of polynomial coefficients and get approximate pole locations. And it turns out if you do that for reasonable values of RC, close enough for slightly greater than 1 by GM2, it turns out the first 2 poles are same as before, roughly same as before. Very approximate result. Now we have obviously a third pole, and it turns out this pole is roughly at 1 by RC into the series combination of all capacitors. This is again a very approximate result, because if you actually try to find it in detail, it becomes too cumbersome. I can just give a qualitative explanation, very qualitative explanation. So let us say you are looking at some medium to low frequencies, wherein the impedance offered by CC is much larger compared to RC. So in that case, we have a large impedance in series with RC. So how can you approximate this as? It's just C. So which means at medium to low frequency this still behaves like this. So that's why qualitatively the first two poles are same as before. Now as you move to higher and higher frequencies, now the capacitors will be dominant. So you can look at the circuit like this. You have C1, you have CC, RC and CL prime. So it seems like you have these three capacitors in series with this. So roughly that's why you have a pole in this location. Again, a very qualitative explanation. Again, this is not the, don't take it to the bank. So then if this is the approximate third pole location, how can you further approximate this as? I have C1, CL prime and CC. C1, do you think it will be a small value or a large value? C1 is a parasitic capacitor, that's small. So which means what will dominate here? 1 by RC times C. Again, very approximate expressions. So at this point, once again, I thought you would have asked me a question. So since you're not asking, I'm asking it back to you. Someone's asking? Pole repeat ho gaya bhai. I mean, the earlier poles were this, right? Yeah. The GM2 by CL was the second. Okay. See, remember that earlier when I didn't do this whole business, how many poles and zeros I had? 2 poles and 1 zero. So the 0 was in the right half of phase plane. So that was a bad thing. Now I wanted to eliminate that bad thing. I tried to do something. So of course the 0 has been pushed to infinity. But in that process, what did I do? So looks like I wanted to eliminate something bad, right? So I tried to do something good. In that process, I added something bad. So what should be the final tally? Yeah, if the amount of goodness you did is greater than the amount of bad things you had done, you're finally safe, you go to heaven, right? So same thing here also. So here, how do you think we can judge if this is better than before or worse than before? Look at the whatever, but I mean, but then also what is the final thing you will be looking at? I mean, I already know I had 2 poles which are same as before. Earlier I had an RHP 0, correct? Now I have this pole. So if I want to make sure that this is better than this, what is the comparison I should look at? I should be looking at the location of this pole and this RHP 0, correct? Now if this pole is located at a frequency much greater than this RHP 0, then it's okay, right? So now we can check it. So let us say I choose RC to be 1 by GM2. This becomes GM2 by C1, correct? Now my old RHP 0, where was it at? This was at GM2 by CC. Now tell me which one will be at a higher frequency? This one or this one? The pole or the 0? The pole is going to be at a much higher frequency. So hopefully we are fine. And that is why you can't go crazy and say that I'll keep increasing RC so much, because you can slightly increase the amount of RC, but as you keep increasing the value of RC, you see that this third pole will start to dominate. That might start to kill your phase margin. So slightly greater than 1 by GM2 is usually okay, but if you make it really large, then these will not be valid, first of all, because I mean, I'll just have to mention these are for, I'll say within quotes, reasonable values of RC. So this approximation will not be fine, and even this third pole, which ideally would have occurred at a much higher frequency, will start to come to a low frequency, will impact your phase margin. Okay. So this is one simple thing you can do to actually get rid of the RHP 0, and it's something commonly done. Cool. So there are other ways also. I'll just briefly mention them, not go in detail. Oops. So again, to understand how to eliminate the 0, you should understand the cause. If you know the cause, you can go and address the cause. 101 of modern medicine. So let's understand what's happening here, right? Again, this is not there, just CC is there. So here, remember that I have a 0 because I have currents flowing in both sides, right? And that gets added to the output at some complex frequency, it becomes 0, correct? And remember that with the Miller effect, all I wanted was a feedback. Now this capacitor is a poor thing, it doesn't differentiate directions. So it can conduct both in feedback as well as in feed forward. That is why you have a current flowing in this direction that can get added to this path. So which means if I don't want to have 0, so I should have only conduction on the feedback side. I should avoid any kind of current that is getting conducted on this side. Okay. If I make sure that there cannot be a current flowing from, let us say, this side to this, then I will not have 0. Is that clear? Then you cannot argue that I have two currents getting added, blah blah blah. And there are a couple of ways in which this can be accomplished. So, I mean, okay, diode and all, if you put, okay, a simpler thing is to, okay, it's a nice suggestion, you want to put a diode. Now you have to make sure this is biased properly, blah blah blah. So, simpler thing that is done is following: you just put a voltage buffer. So this way you have the feedback alone, but not feed forward. Now, of course, if you have in practice, you can't make an ideal buffer, so it will have its own output resistance. So the moment you have an output resistance for the buffer, things will be slightly different. I'll give it as a practice problem to work out where the zeros will be in this case. And of course, now the pole locations also slightly get changed. Let's not worry so much. Now, what we have done is basically added a buffer in this part so that we can kill the feed forward conduction. So just like how I can add a voltage buffer, what can I add? Okay, I thought I was leading you to the correct thing. Just like you have a voltage buffer, what buffer I can add? You can also try to add a current buffer actually. So even if you put a current buffer here, again same thing, right? Current can only flow this way, not the opposite side. And how do you make a current buffer? Simplest current buffer, common gate. So you can try to do that. Again, just drawing the small signal equivalent. We have to make sure it's biased with proper things. And it turns out if this is an ideal current buffer, if it's an ideal current buffer, what should be the input resistance? For ideal current buffer, this should be infinity. Here, approximately what is the input resistance? Assume that the drain is at a much smaller impedance. This is of the order of 1 by gm if you ignore R0 and stuff. So if gm is infinitely large, then once again the 0 would have been gone completely and your poles will be roughly same as before. But with finite gm, then things become slightly tricky. Again, I don't want to spend time on the pole locations with this case. Okay. And it turns out this no idea of introducing a current buffer here was first introduced by Bhupendra Ahuja. So this is often referred to as Ahuja compensation. I'll give a couple of problems in the practice problem set so that you understand what happens here. And a fun trivia is Ahuja was actually an alumnus of IIT Kanpur. So maybe he was sitting right in this place and listening to some lectures. Cool. So that's mostly about this Miller. And one variant of this Miller compensation, or I would say this notion of keeping the poles far apart is this. See, with Miller compensation, what we had done is we had two poles which were close by. We may maybe draw it here. Let's say we had two poles close by. We made sure one went to a very low frequency, other went to a very high frequency. Correct. Now, sometimes what is also done is the following. Let us say you want to just push one pole to a very low frequency. What is the simplest thing you can do? Let us say you had the same two-stage OTA, a simpler case. So if I call it G1, C1, G2, C2, where are the poles now? Where are the poles now? What? G1 by C1, G2 by C2. Let us say I want to push one of the poles to a very low frequency. What is the simplest thing you can do? Yeah, I mean there is already capacitor. So if you want to push the pole to a low frequency, what can you do? You can go and put a capacitor. Let's say you go and put a large capacitor. Let us say here. Then this becomes C1 plus whatever extra capacitor you added. So this moves to a low frequency. Right? I mean, we through Miller effect we put a capacitor here, so the apparent capacitance look bigger, but instead you can put that big capacitor directly here also. So, but if you do that, only one pole moves to a low frequency, other pole remains at the same location, right? So that is a drawback. So sometimes this is also done, and this is called as dominant pole compensation. Again, the notion is the same. You keep the poles far apart. In Miller effect, we did the following. We put a Miller cap here that made sure one moved to a high frequency and one moved to a low frequency. So we got a double benefit. Whereas in dominant pole, you just put a large capacitor somewhere so that that pole moves to a low frequency. So sometimes this is also done. Cool.